At this point in the semester, you're kind of programmed to think about studies in this way. We take a group of patients and we give them a drug, and then we measure some variable. Well, then we take another group of patients and give them a placebo, and then we measure that same variable. Then we compare the change in variables between those two groups. Well, with correlation and regression, you're going to have to get out of that mindset just a bit. With what we're going to be discussing today, instead of having nice, clean data we can evaluate cause and effect between the variables, we're actually just wanting to look at the relationship between those variables. In fact, we can't even assume causation with the types of analyses we'll be talking about today. What that means is we might look at how age relates to blood pressure. So we want to look at that relationship between the variables. So as age increases, what happens to blood pressure? So we take all of our patients' ages and their corresponding blood pressure, and we essentially plot them on a graph. Patient 1's blood pressure was this, and patient 2's blood pressure was that, and so on and so forth. This type of graph is helpful in visualizing these relationships, but for studies where we don't evaluate the correlation and regression, they're not really used. Our data would look a little weird. If we were trying to compare means using a t-test, right, then we just need the actual mean difference. This graph doesn't help us understand the information any better. With correlation and regression, we aren't looking at the mean, median, or the mode. So how do we compare data in a graph like this? We end up talking about this line of best fit and how well our data fit to that line. If they fit very closely, we say there's a good correlation, and the numerical value we assign to that relationship, which we call rho, will be closer to 1, or -1 if there is an inverse relationship. If there isn't a strong relationship, if, let's say, the amount of carbs consumed daily neither trends upwards or downwards in relation to age, then we'd expect our rho value to be closer to 0. And that graph looks a lot messier. You can tell that there's no easy way to fit a line of best fit within those data. With regression analyses, we can use this line of best fit or regression line to actually predict variables. Importantly, from a clinician standpoint, we may not always be given that line of best fit when provided with a study that uses regression. If we do, it'll be in a slope-intercept line formula, so y equals mx plus b essentially. We can plug in our x values and get a prediction for y. So that's a quick introduction to correlation and regression analyses. But there are a couple of really important things to note when it comes to correlation and regression. So number one is we still can't infer causation from any of these tests. You often hear correlation is not causation. But even for regression, despite its ability to predict a variable, it doesn't mean that the relationship between the independent and dependent variable is a causal one. So regression is not causation, works just as well as correlation is not causation. In regard to regression, remember, we really like regression because we can predict variables, but we can only predict data within a range that we've already studied. And this is an important concept, so let me give you an example. So for example, the effects of alcohol on cardiovascular risk are fairly well described. So let's say you and I, actually conduct a study ourselves, and we call it the Perkins and you study. Since it's just me and you, we don't have a whole lot of money to recruit a bunch of patients and collect data from them, so we only recruit patients who drink between 0 and 2 beers a day. The data from the Perkins and you study suggests there is a strong relationship between the number of alcoholic beverages per day and decreased cardiovascular risk. So let's say we conducted a simple linear regression, and now we want to predict how much lower your cardiovascular risk would be if you drank 2 beers a day. So here's our regression line. So if we input 2 for our x variable, for the number of beers we would consume on a daily basis, This gives us a cardiovascular risk reduction of 18%. Now some might say, and hopefully it's none of you, how much does 8 beers a day decrease this risk? Well, that would be 72%. Is that right? Of course not. So let's take another look at our graph again. We only ended up recruiting patients that drank up to 2 beverages per day. But if we extend this out, in the actual studies, what we see is a J-curve. The data from this study actually suggests that the data are not linear. Had our study, Perkins and you, included patients who had consumed 8 beers a day, we would have seen that the cardiovascular risk would have actually gone back up. This is why our study, Perkins and you, illustrates a very important point, that it's important to not attempt to predict variables that were not included in our study. Our study simply can't predict the cardiovascular risk for individuals who would consume 8 beers per day. Another important point is that rho values, by themselves, they simply quantify a relationship. But it's important to note that the magnitude of the relationship between rho values are not consistent. So if the relationship between age and weight is 0.4, and our rho value for age and the risk of myocardial infarction is 0.8, it doesn't mean that we can say that the relationship between age and myocardial infarction risk is twice that of age and weight. Making that comparison is not correct. Another important concept is our coefficient of determination. So our rho values can be squared to find this coefficient of determination. Don't get hung up on that term too much. Just know that it quantifies how much one variable accounts for another variable. And this is actually a pretty useful tool. For example, if a study we conduct provides a rho of 0.4 for the relationship between age and weight. So as age goes up, weight tends to go up as well. Well, if we square that value, then we can see that age actually accounts for only about 16% of a patient's weight, meaning that nearly 84% of someone's weight is actually accounted for by things other than age, like diet and exercise. Which is great because now we can tell our patients that changing their diet and exercise will help to improve their weight even as they age. Hopefully this video gave you a heads up on what to expect for the lecture, and you can come into class having some idea about what to expect. I'll see you then.